Welcome to the Non-Destructive Testing and Condition Monitoring Detecting Hidden Flaws webinar. Our speakers today are Clough and Jon Hughes. Once both Matt and Jon have finished their presentations, we encourage you to use the Q&A function to ask any questions. First up is Clough, who will be talking about non-destructive testing at MPL.
Good afternoon, everyone. We're going to talk today about the work at MPL that we do, particularly in the materials group, regarding non-destructive testing and condition monitoring. So first half of the presentation will be on non-destructive testing, which I'll do, and then I'll hand over to my colleague Jon for condition monitoring later on. If you're not aware of MPL, perhaps it's your first interaction with us, with the UK's National Metrology Institute. It's a public corporation owned by the Department for Science, Innovation and Technology. All of the work you will see today is based in Teddington, at the main site in Teddington. But you can see that there's several locations across the country and various partnerships with universities. So the important thing to remember about MPL, as it says at the bottom there, there's a range of different groups that do a range of different science. So although we're talking about the non-destructive testing that we do in the materials group today, there's bound to be topics that are of interest from the other scientists across the lab that do non-destructive testing but don't do it under the specific banner of materials. So just keep in mind that this isn't all that there is. There will be other work that goes on in those areas. But if we focus down on the materials group, this is just a summary slide of what the materials metrology looks like in our materials group at MPL. So various length scales worked on, micro, nano, up to macro scale. Again, keep in mind that although we're talking specifically in the bottom right-hand corner, the non-destructive evaluation and structural health monitoring, we can do work with all of these other materials characterization techniques if you want a fuller piece of work carried out. So focusing down on those areas that we saw in the previous slides, hopefully if you've signed up for this webinar, you'll have seen our ebook on our web pages. If not, I'd encourage you to go and download it, because that gives you the technical information, and that will go along well with the high level that we're talking about in these presentations. So as I said at the start, we're splitting it into non-destructive testing, which in our case is lab-based, and we'll go through that range of techniques we've got to do non-destructive testing in the lab in the slides following. But the difference to draw here between the lab-based entity and the condition monitoring is the lab-based entity is all on commercial off-the-shelf equipment that we would use to illustrate how measurements could be made and provide that insight into an inspection scenario, whereas the condition monitoring that we carry out is trying to take those lab-based techniques out into the field and apply them on larger structures, and that's what Jon will be describing to you later on. So if we look at the non-destructive testing that we do, the work that we carry out for customers, for UK industry, tends to be based on a new material or a new component or a new production process, where someone might come to us where they know there's a defect or an underlying quality in the part, but don't know how to locate it or determine its severity, or they have encountered an issue and just require some sort of initial assurance and a pathway to providing better quality control of their components. So what we would do is assess the problem, assess the material that has come to us, and down select a technique or techniques that we think might work from our selection. So this slide shows the range of techniques that we have available, ranging from largely immersion ultrasonics in the top left corner, with some contact ultrasonics to confirm what we're seeing in a more industrial relevant way. And that has a range of different frequency probes that we can use to identify different sizes of defects and deal with different materials that might have different attenuation properties. Then X-ray cabinet for conventional X-ray. We use eddy current and magnetic induction generally for non-conductive coatings on conductive substrates. So if there's an issue where we can apply that technique. And then the bottom row, microwave, laser chirography and thermography tend to be techniques we use in materials that are less traditional. So instead of being your metals, we're talking about new materials, composites, and those sort of emerging materials that we might have to use a different technique for, that either doesn't give us enough contrast in X-ray or perhaps doesn't like to be immersed in the water bars that we have to use for ultrasonic methods. We have all of these techniques so that we can provide a range of possible answers. We can also then use them together to compare the data to see what gives us the best results in a particular material or for a particular defect type. We would typically operate that as a consultancy. If we found a method that worked with these more basic application of techniques, we would advise on where and how you could apply, how you could go out into the wider UK industry and find that solution to incorporate into your production process or into your quality control. The benefit being that we don't, because we've got all of these techniques, we don't need a particular one of them to work, or indeed none of them can work, and that's still a solution for us. We've can use that as the answer. So the rest of the slides will go through a bit of what the imagery we get out of these techniques, and generally it is imagery that we will be delivering with interpretation. The ultrasonic facilities we have is a large C-scan tank where we can do flat panels, panels with curvature, or parts of curvature, and surface following, and for defect detection. So the top line of images are a front wall interior content and back wall image of a glass fiber curve sample that we've put artificial defects in. But of course, we don't just look at the artificial defects, but we can use that to gauge the sort of size of defects we might find in these parts. We also have this scanning acoustic microscope, which we can use higher frequency probes with a better time resolution and slice, do tomographic slicing in 2D through those samples to see what features are in a material and where in the depth they occur. So that's these images across the bottom, just showing a slice through a pellet of metal in that case, showing the porosity throughout. So tend to use those. I mean, they're clearly lab-based. We're not going to be using those out in the field, but they give us that assurance that we know what we're seeing in those materials. We can then look at those images and highlight where defects have occurred, either in these artificial defect type situations where the top rows an amplitude map and the bottom rows looking at time of flight, so we can identify those artificial defects, or in a real defect situation we can see how far the damage in this case has spread from an impact site. If, as I say, we feel that a situation might require not just the high resolution scanning in the lab, but a view of techniques that can be used on site, then we have handheld ultrasonics we can provide examples for. We have a lower frequency pulse velocity system that we can use for attenuative materials. And here again, we've just got standard equipment for eddy current and magnetic induction, as I say, usually used as coating thickness testing for us, if those are applications you're interested in. So the ultrasonics is, so long as it goes in the water bath, we can do it on most materials. With the eddy current and magnetic induction, you need electrically conductive. If we need to compare against something, we might use the X-ray cabinet if we want a view of material that might be difficult to do ultrasonics on. So this mixed material here of plastic pipe with a metal spray applied, we can see we would use it in these situations to see the contrast of the metallic material against the plastic material. So those two are fairly, or those ones we talked about before, fairly conventional. We could use them for a variety of materials. The following techniques, the microwave viscography and the thermography, we would tend to use them for materials that, when in the case of microwave, it's a non-conductive material. In the case of viscography and thermography, we'd use it for composites in particular. So the viscography equipment we've got an XY scanner with a microwave probe that can do several different frequencies, so we can access different wavelengths that are sensitive to different size defects. And here your imagery gives you things like voids or water ingress. Again, we can look at calibration style panels, or we can look at a real material. And because we're examining through the bulk of that material, we can look at it volumetrically and see what's happening. This imagery shows you the air voids that are within that material between the front face and the core, and we can use the mathematical relationship between the two receivers we've got in there to amplify certain signals to see whether that can give us more contrast in our results and show up those defects. So we've used this in the past quite effectively for, as I say, non-conductive materials, or for detecting a metallic material in something that where we're not expecting it, because we're going to get a reflection of the microwave from that metallic material. We can then investigate the same sort of material with something like laser viscography. So we have a standard Dantec dynamic system with a couple of heaters that provide a impulse to the sample that causes it to be stressed, and then we're monitoring it with a camera and viewing what the speckle pattern of the lasers we have here, divergent laser diodes there, put a speckle pattern on it, and we're seeing what the difference is as it's stressed. Generally we use heat, but we could use other excitation methods. Again, you can see it quite nicely on a calibration style sample, but also in that real sample, we can see those air voids are showing up in that material. Thermography, we've got a few different options. We have a flash thermography system, so a millisecond duration flash onto a sample to introduce that impulse of heat. And then we're monitoring the surface with the thermal camera to see if there's any disruption of that heat flow. That can give us imagery such as this in the black and white. Again, this is showing that air void below the surface of the skin on that sample. If it's a larger sample, we might use flood lamps and a different thermal camera to obtain the same sort of information, where we're monitoring it in heating and cooling to see whether there's any disruption of that heat flow. Often what we're asked then is, can we also show that in a way that's more cost effective for a customer? So the setup we've got here, the heating's fine, but the camera is a research level camera that's probably outside the reach of large part of industry in terms of cost to make that inspection cost effective. So we would do tests such as this with more of a building inspection style camera to show that whether it can be done in a more accessible way. So a lot of our work is finding the defect, but then assessing whether there's an accessible way for the customer to use that in their daily inspection or in their daily process. You'll notice that I kept saying about the same sort of material. We can use that information with those different techniques to highlight what technique is going to be best as a non-destructive testing technique for that particular application. What is going to be most cost effective, what's going to be giving you the best result. Perhaps you've got a process that already introduces heat. In that case, adding a thermal camera to the system isn't going to disrupt it too much. Or we can just use it to confirm what we're seeing. So in all the images here is the high-end thermal camera in the first column, the same data showing on that more cost-effective camera, and then the shearography and microwave, so we can see the same features and all, and pick the method that's going to be most appropriate for you. So I've hopefully given you a summary of what we do, the sort of problems that we try and find NDT solutions for. In order to do that, we've got this range of techniques. As described, they're used and intended to be a base level so that we can show detectability, and then we would assist the customer to find, well, first off, the most appropriate, as I say, for your material and defect type with our equipment, taking into account if there's access requirements or surface treatment requirements, in order to de-risk the search for an NDT solution that might be able to be procured from the market as a whole, rather than us providing that solution continuously as a service. The benefit of MPL is we can work, as you saw, with that range of other techniques we've got in the materials group. So if there are complementary techniques you wish to use with your material part, we can access those. And in wider MPL, as I mentioned at the start, there's lots of other science that goes on that is non-destructive but isn't under the ban of materials. So as I say at the bottom, contact us if you've got a problem that you think non-destructive testing would help with, and we can provide guidance and do some work. That is the end for me for non-destructive testing. So I shall pass over to John to do the condition monitoring section of the talk. Thank you.
Thanks, Matt. Let me just share my slides. Okay, thanks very much. That was great. Thanks, Matt. So I work in a slightly different field to Matt, which is related. And essentially, I use a combination of the techniques that we use in the laboratory, but I've taken them out of the laboratory and I use them into the field, and that's what I'm going to speak to you about today. So much of what we do revolves around imaging, and specifically a technique called digital image correlation. If you're not familiar with digital image correlation, it is a way of tracking pixels in an image. In the laboratory, and you can see a picture of a fairly complicated setup on the right there, we use it to make strain and displacement measurements on test machines. So we'll have a speckle pattern typically on a specimen. And there's 3 specimens in the middle there with different levels of speckle on there. And we'll use DIC to track that specimen as we either pull it apart or squash it in the test machine. And essentially what we're doing is we're using the pixel changes on the CCD of the camera to make that strain measurement instead of using something like a strain gauge. So it's a non-contact technique. So originally this was just done with single dots, like a video extensometer, if you like. And as the amount of computing powers increase, we can now do full frame digital image correlation. So we can actually look at the strain map across the entire specimen. And if you throw enough computing power at it, we can actually do it on large scale structural examinations on very big structures. And we can do it over a very long time period as well. So that's mostly what we do. We have another couple of techniques that we can use in the field as well. Again, very much related to the techniques that Matt uses. An example on the left-hand side here is where we've used thermal imaging in concrete structures. So there are many concrete tunnels being built at the moment with Crossrail and HS2. And in this example here, what I'm showing you here is where we have a thermal imaging camera pointing at this concrete block. And at the same time, we're projecting that image back onto itself. Now we can bring out what's going on behind the surface by adding some heat, as we would do with thermography. And in this case, what we've done is very lightly sprayed the surface with water and waited 30 seconds to a couple of minutes. And the heat output is different on the surface when there's something behind the surface present. So in the case of this block that we have here, it's very easy to see because this has some standardized defects that we've put into the concrete, and you can see them start to appear fairly quickly. And we can use this technique for very rapid detection of subsurface features like this. And we typically find those in bridges, any reinforced concrete structure like flyovers. And we've used something similar on a Hammersmith flyover, and we've trialed it with HS2. We can also carry out digital image correlation like techniques to quantify changes in non-RGB images as well, and we can track those over time. So we don't necessarily have to do DIC just in the RGB. We can track shape changes as well in the X, Y, and Z plane. So we're making dimensional measurements with it. And likewise, we can also do that with 3D laser scanning and LiDAR, which are other measurement techniques. So we can extract the physical dimensions from there and track how it changes over time in a structure. We can also do it with ground penetrating radar, or GPR, and that tells us something about what's going on in the subsurface. And we can also do it with hyperspectral imaging. So that's when we're looking at the non-visible light spectrum, so either infrared or ultraviolet, and that can tell us a little bit about the chemical makeup of the surface. And again, we can use a DIC-like technique on that and track how that's changing over time. So typically, we can use 3D laser scanning and LiDAR to build up 3D models of structures, but we can also do that with stereo light as well. And that's what we've used in the next project that I'm going to show you. One of the issues with laser scanning and LiDAR is the challenges with the resolution and positional accuracy, which we've overcome with one of our trolleys, which we use in tunnels, which is called DifCam. So that's a digital imaging for condition asset management. And this is a project that we've done in conjunction with Network Rail, and we've had some help from Mott MacDonald and Omnicom, who are contractors on the rail, who enable us to get out onto the rail while we concentrate on the science side. So DifCam is it's a tunnel surveying trolley for Network Rail for in the railway tunnels. It's a prototype. It's a single camera prototype, essentially, for a multiple camera train mounted system that Network Rail will be building. And it uses a stereo line scan camera with very high power lighting. So it takes a single pixel wide image, which is around 7,000 pixels tall, and it's two of those ever so slightly overlapped. So it can measure both RGB and also height as well. It's on a counterbalanced boom, and it has several camera positions. So the trolley that you can see down on the right-hand side there, that has the boom mounted on the right-hand side of the trolley, and we can also put it on top of that tower that you can see there, and extend that up to about 5.5 meters. So we can quite easily reach the top of the tunnel, which is typically around 6.5 meters up in the air. So we take the images in overlapping stripes. So we'll set the camera in one position, we'll wheel it along the length of the tunnel, reposition the camera, come back down the tunnel, and as and when we need to, we'll then need to move the boom onto the other part of the trolley so that we can then either swing it round or lift it right up to the top. And as I mentioned, it collects a combination of both image and height data. Why are we doing this? And the simple fact is that Network Rail have got a very large portfolio of aging tunnels. They're all Victorian brick tunnels. They're all in a terrible state of repair, and they simply don't have the resources to inspect all of them. They're currently inspected by quite skilled inspectors who will walk through the tunnel at night when the line is closed. They'll have head torches on, and they'll typically be looking for any defects they can see with head torches, and with long sticks they'll be tapping the surface to listen for any voids behind. So DifCam is a way of quantifying those changes and essentially taking boots off ballast so that most of the inspection can be done away from the tunnel. So exactly how do we do this? Well, I've mentioned timescales. So most of the tunnels that have to be inspected will need the line to be closed for the inspectors to walk through, and that means they have a very short window of time to do this. So it's exactly the same for us when we go on the line. So we have quite a lot of preliminary work that we have to do before we go there. So we calculate all of the camera positions to some degree in advance, and the image on the top left there is just a little schematic of where we're going to be putting the camera boom and the camera angle, and checking that the tunnel wall is going to be in focus before we go there, so we're pre-prepared. Once we've taken all of our image stripes, essentially we can stitch them together, and we end up with a panoramic image of the inside of the tunnel. The big image in the middle there is the first 10 meters of that tunnel that you can see up on the top left. we've effectively laid it out flat, like in the image on the bottom left there. So it's semi upside down. And we treat it as a flat image with height data on there. So this was from the first time that we ever did one of these tunnel scans, and you can see that there are a couple of black lines and black areas on the image, and a few blurred bits, and I can talk you through exactly what happened there. So the tunnel portal is on the left-hand side, and we're moving into the tunnel as we move to the right. So the right-hand wall that you can see in the image on the left, that's at the bottom of the image, and the left-hand wall is at the top of the image. As we go into the tunnel, you can see a couple of long black lines, and that's basically where we didn't have enough overlap on the camera. So we've got missing data there. The black box on the right-hand side in the middle there, that's actually where we got some water on the lens of the camera. And we decided to abandon the run because we were under time constraints, and really because we scanned around 80 meters of this tunnel, we didn't have time to redo that. So we decided that since the top of the tunnel is the most difficult place to get to, that we'd abandon that bit and just stick with what we've got. So once we have these panoramic images stitched together, we can start to pull out quite a lot of information from this. In the top right there, we've got the height map from the tunnel, so you can see all of the individual block work. And the black and white image in the middle there is where we've done subsequent runs with a time period between them. And what you can see in the difference between the black and the white are areas of low correlation between the images. So that tells us that something has changed in the image over time. We can track that either as movement or as depth or as an RGB change. And that can tell us an awful lot about what's going on in the tunnel surface. So that could be cracks, that could be bricks that have moved, it could be mortar regression, it could be changes in the shape of the tunnel due to subsurface effects, all sorts of different things. And all of this can be done outside of the tunnel and basically in the inspector's own time in the office, rather than having to do it on the spot. So exactly where do we put all of this data? Well, it goes into a GIS system, which is held by Network Rail. So that's the image down on the bottom right-hand side, and it's effectively overlaid onto a map, but unwrapped flat, fairly similar to the way Google Maps holds its data on there as well. Now, in terms of data size, a tunnel that's around 700 meters long will generate an image which is in the order of around 250 to 270 gigapixels, and that's around 10 terabytes in size. We haven't just used DIC with DIFCAM. We've also combined it with ground penetrating radar. So on the Bluebell Railway, they have a very similar tunnel, very similar brick tunnel to all of the other tunnels on the Network Rail system. And we wanted to scan an entire tunnel. And this is very difficult to do on a live network because of the time constraints. We will typically only get around 8 hours of a night time to be able to carry out one of our scans. So even on two subsequent nights, two subsequent possessions, that is, we'll only be able to do a short section of tunnel. On the off season at the Bluebell Railway, they don't run trains during the week, and this was a massive attraction for us because we could spend 5 days straight scanning the entire inside of the tunnel and just working out what was involved in collecting and managing that amount of data. Now, while we were there, we also invited a company who had worked on a similar funding scheme to us with Network Rail, who carry out large-scale ground penetrating radar scans inside tunnels, and this was Quantum Structures with their TSIR system, and that can detect anything in the subsurface up to about 2 or 3 meters underneath the surface. So they took 3 linear scans, so in the direction of the tunnel, at the 9, 10, and 11 o'clock positions, while we had our RGB and height data. So after a little bit of realignment, so that our DiffCam system uses a tachometer wheel to measure its distance forwards and backwards, which is quite accurate and repeatable, whereas the TSIR system relies on the road railer driver driving at a constant speed. So the resolution is a lot coarser, and it's not quite as, in fact, it's not accurately placed at all. It's very much estimated. However, we had lots of fixed features in the fixed height features inside the tunnel, which allowed us to be able to align the 2 data sets, and that's what we did. We found a very interesting subsurface anomaly. In one section, there was the 3 images in the middle here. It's not very obvious from the top one that the center section of the brickwork actually sticks out from the wall by a whole course of bricks. However, our height data shows that quite clearly. So we know that is a fixed height feature. What we weren't expecting to see was on the GPR scan, ever so slightly below the surface, it was showing that the kind of feature that would suggest that the brickwork was not actually attached to what was behind it. So we would call that ring separation. That's a very important thing that that Network Rail have been looking for. The key thing here really is that ring separation is not an easy thing to spot unless you're tapping the wall and you're an inspector with a trained ear. And we've found a more effective way of finding it, and a more rapid way of finding it, which doesn't necessarily need the inspector to be in the tunnel. In this case, this enables the inspector to find it on the GPR and RGB scans, and then he only needs to go to a certain place in the tunnel to carry out his inspection. He doesn't need to inspect the entire tunnel, and this is a massive time saving for Network Rail. Additionally, on top of this, we have also mapped the tunnel geometry. So we have to correct all of our images because they're effectively flat images taken from a curved surface. So we correct the shape of these, and that's what you can see on the right-hand side. And we've also overlaid the GPR scans, not to scale, but to show basically where they are. And this is what the tunnel inspector uses to go in and find those areas. And we can clearly see the correspondence here between the joints and the ring separation. So the dark section on the top of the GPR scan there is where we can see the ring separation. Another project where we're using digital image correlation in a tricky to access area is at Sellafield. So this is the HAZE system, the high accuracy inspection system. And this looks deep inside the nuclear waste stores at Sellafield. The newest store at Sellafield is 16 meters deep, and it contains low-level waste from various previous nuclear activities. That waste is in there for 100 years, and it's sealed in there, and you can only access through some ports in the floor at the top of the store. They're quite small, and it's currently done with a camera on a stick, so the inspector feeds down a camera on a very, very long stick and has to keep screwing on extensions, and it's just a sort of visual view of the inside. Now, we've changed this significantly by using a system where we can lower the camera down to known positions, and in the X, Y, and Z planes, we can take repeatable images, and we use an item called a roller tube, which is a bistable composite tube, which is effectively like a fiberglass tape measure. And that takes down a pan tilt and zoom camera so we can get close in on everything. And again, it has very powerful lighting on it. And it's used primarily to monitor the corrosion in the store, but we can also see the changes in shape and positional and anything else that's going on inside the store there. So what challenges do we have going forwards? Most of our challenges are around data. As I mentioned with the railway tunnels, the data sets are enormous. So there are logistics challenges involved in handling data sets when they're around 10 to 20 terabytes in size. You can't just upload them to the cloud. They're even quite difficult to physically get off the computer on the machine on DiffCam because they corrupt very easily. So we have to typically carry around 3 copies of everything. So it's never a 25 terabyte data set. It's often 75 terabytes because of the number of copies that we have to keep. Transporting that data is difficult because, again, it gets corrupted on hard disks when they get knocked around. The storage and the backups is challenging in itself simply because of the number of different backups that we have to keep. I mentioned that we have to have 3 of everything really to be on the safe side. Typically, to then work on something, we'll make a copy, work on the copy, and that then adds another 25 terabytes or more to everything. Simply processing and carrying out the image comparison for digital image correlation on giant data sets like this is also a massive challenge. And it can take upwards of 80 hours or longer to process the data and then to run through the digital image correlation on a whole tunnel's worth of data like that can take days. Uploading and downloading this data is currently very, very difficult across a network because the bottleneck is typically the network. And that also means that supplying our data set to the clients, typically Network Rail in this case, is very challenging because we can't just transfer it to them. We have to work out ways of sending it over to them on hard disks and making sure that is secure data as well. One of our other challenges is just how quickly the technology is evolving as well. In the years that it's taken us to develop and take the machine for Sellafield through the UKCA marking process, much of the technology on board is becoming redundant very quickly. It's moved forward so quickly. So we have to think about how we're going to take this forwards ourselves. The camera types are changing rapidly. So whereas when we first started developing the machines, all of the cameras only had 2D capability, and now they almost all have 3D imaging technology. Much of what we use on a larger scale is possible on your mobile phone in your pocket. It's just harder to access. But we need to keep this in mind because if we can use similar technologies, then we can really improve the way that we carry this out. And probably our biggest challenge going forwards is likely to be artificial intelligence. And not because it's likely to take over what we do, but possibly the opposite, because artificial intelligence really relies on having a data set that it can learn from. And there are no data sets for tunnels. We're developing the first ones. And really the challenge involved there is if you were to use an artificial intelligence to pick out defects, would you trust it when it's only learned one data set? And the answer to that is currently no. So we have to treat this very carefully. So the type of intelligence that we use on our data sets are very, very much more simplified. They're much more geared towards image recognition and those sorts of techniques. So I think that brings me to the end of what I wanted to present you. So I'd like to open up the panel to questions. So if you have any questions, please put them into the Q&A area, and we're happy to answer anything that you ask. Matt, do we have any questions in there already?
Question about your DiffCam work. When you're using the railway tunnel trolley, how do you line up images so that they match?
That's a good question. So on the DiffCam trolley, we actually set down a reflective marker for the start and finish point, so that we have a fixed point on there. We don't need to use that. The tunnel itself has a number of fixed features inside it that we can use for start and end points. However, we prefer to have a fixed one that we as a known datum. So the sorts of fixed features that we have in the tunnel that don't really move much are the tunnel portal. An example of the Bluebell tunnel, there's the section that sticks out. That's a fixed feature. There are a number of refuge points throughout the tunnels as well that we can use to realign other data sets that we put on there. And that's basically what we used to align the GPR data set. So we know inside the tunnel that we have those refuge points where workers back in the day could move away from where a train was coming through. They show up as dark points on the GPR because they're at a different depth to the main face of the tunnel. So although we do use fixed points, we don't have to use them.
Okay. There's a question of do you work on aircraft, which I suppose we could answer for both sections. For the NDT, we have done work on aerospace structures, mainly if it is an issue that doesn't have a current solution. So if it's a standard aerospace inspection, then we would usually leave it to operators that are already working in those sectors and have the detectability limits on those that the providers are happy with. But we have done consultancy work on that before, and I know we've been asked about imaging on aircraft structures recently for the condition monitoring work. I don't know if you have any thoughts on that, John?
Yeah, I mean, we get asked a lot. So for the large scale stuff, particularly for the wing structures, we get asked a lot whether we can do this with drones. This is an area we'd like to try drones, but they're challenging. From a positional perspective, a drone presents specific challenges in that you don't really know where it is, and they're not very stable, even with gimbals. And that introduces complications into things like digital image correlation. Additionally, with the drone, you can't really carry a very heavy payload, and that either means you have to use a very large drone or you have to use a much lower resolution camera, which again reduces the efficacy of things like digital image correlation or any other parallel technique you might be using with it. So it's certainly something that can be done, but it presents its own challenges.
You've got Rob from Summerfield enjoyed your
Thanks, Rob.
presentation and is looking forward to being deployed. We've got a question about how do we get in touch with MPL, so I will put a link in the Q&A at that question that links to our landing page, and we'll see. I think our last slide has that detail on as well.
We do have a final slide here.
The easiest way is to go to our web page. You could download the ebook from there, or if we use the contact us form on that site, that goes into our system and will be routed to us. So if you do have any projects that you're interested in working with, or just need any extra information, do use the contact us on the website, and we'd love to hear from you. Don't think there's any more questions at the moment. So we should probably leave it there. Thanks very much for your attendance, everybody.
Yeah, thanks for listening. Hope you enjoyed it.